Hi guys, so this is video 2 on sketching the graph of a rational function. This way though we're doing it by sine wave. So I already have the graph sketched because of what we did before based on assumptions and vertical asymptotes, but this time I'm going to prove it to you through a sine wave. And sine waves are really important in 1050 calculus to make things go further. Okay. So when I was younger and we used to do sine waves, we would have to plug in a number that's in between the two and then see if it's positive or negative. That tells us if it's going to be below the x-axis or above the x-axis. But actually there's a sine wave process that can be proven, and you don't actually have to plug in and chug. You can just actually do the process and it comes out correct. So when you do a sine wave, where we talk about positive and negative, where the graph can change from positive to negative, deals with the x-axis. So things that affect our x-axis are our x-intercepts, so that we put on our sine wave, and our vertical asymptotes. These are the two things that we put on a sine wave. So according to our example 1 that we have in our notes here, we have an x-intercept of 1, a vertical asymptote of 3, and a vertical asymptote of -2. So we have 3 numbers to put on the sine wave, and you want to make sure that you put it in order. So we have -2, 1, and 3. So I'm going to show you this idea right here. If I did -2 when I was younger, I would plug in a value of, let's say, -3, and I would say, well, that would create a negative up here, that would create a negative up here, and that would create a negative right here. Negative times a negative is a positive, but a negative over a positive is a negative. So I would see that this became a negative right here. But there's a pattern that always happens. So here's what we do. For every number I see, what I'm going to do is put my pencil right on top of it. Everything to the left of that number is negative. Everything to the right is positive. So for that -2, I have a negative, then everything on the right is a positive. Okay? That is just for the -2 though. I have to do that then for the 1. So I put my pencil there. Everything to the left is negative. Everything to the right is positive. And I do that for the 3. Everything to the left is negative. Everything to the right is positive. And then I multiply straight down. Negative times a negative times a negative is a negative. Didn't we say that was going to be a negative? Negative is a positive, times a positive is a positive. Negative times a positive is a negative. And positive is a positive. Now let's check this out, and then I'm going to show you where it could be tricky. Okay. So -2, right? -2 to the left of -2 should be negative, right? Well, is it under the x-axis? Yes, it is. Where 1 is right here. To between -2 and 1, it is positive. So between -2 and 1, is it above the x-axis? Yes, it is. Between 1 and 3, it is negative. Is it below the x-axis? Yes, it is. And 3. And to the right, it's supposed to be positive. Is it above the x-axis? Yes, it is. So it works. Now, there are certain cases that we need to think of tricks. And we're not going to deal with any tricks today on our homework or practice, but tricks is the function negative. Because if the function is negative, you have to add in a row of negatives, remember? Because a negative function means it flips. The other situation is if we had our exponents being even or odd. As you can see, they're all to the first, so we only have 1 row of each. If they're odd exponents, we only have 1 row. But if they were even, 2, 4, 6, 8, if they were even exponents, we would add 2 of that row. So if I had an even exponent right here to the 3, the row of 3 that I made, which was this one right here, I would put it in again. And that would change my function a little bit and how it looks. Let's see if it adds up with the other 2 examples that we did together. So the next one we did for example 2, we had f of x equals 2 times x plus 1, x minus 1, all over x plus 2 times x minus 2. Now remember, in our sine wave, we're going to do both vertical asymptotes and our x-intercepts. So we have 4. 2 x-intercepts, 2 vertical asymptotes. Remember to put it in order. So -1, oh, -2, I almost forgot it. 1 and 2. All right. So I'm going to have 4 rows because this function is not negative and all of these exponents are odd. Okay, so at -2, everything to the right is negative. I mean, left is negative, right is positive. So that's the row for -2. -1 would be negative, negative, and then positive toward the right. At 1, I get negative, 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 positive, positive. And for 2, I get negative, 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 positive. Whew. 4 negatives make a positive. 3 negatives make a negative. 2 negatives make a positive. 1 negative makes a negative. All positive makes a positive. So let's double check now with our graph. Okay, so to the left of -2, which is right here, is positive. Are we in the positive value? Yes. Now, it could be tricky, right? Because we could have gone here and cut down, right? But then there would be an x-intercept. So this really tells us where it's going. Between -2 and -1, so -2 and -1, it is negative. Look, it's below, so that's good. Between -1 and 1, it's positive. Yep, it was above. Between 1 and 2, it's below. That works. And to the right of 2, it's above. Yay! Okay, one more. And then you can test out your stuff. Try to do a practice here and there just with the sine wave instead of doing the assumption because of the intercepts and stuff, okay? So if we look, a reduced function, because that's what we need to focus on, is 1 over x plus 3, which means we only have a vertical asymptote at -3. Our function's positive, so we don't need a row of negatives. And x plus 3 is to the first, so we only need 1 row. And there's our 1 row. That was pretty easy, right? Okay, well, if we look at our graph, if we look at -3, to the left of it, where is it? It's below. It's negative. And that matched with our sine wave. And to the right, it's positive, which it matches with our sine wave. So these sine waves really are a good strategy to use. But remember, in the sine waves, you can use this with other functions, not just rational. And that's why it's so important for 1050 and calculus. All right, give it a try, guys.